All right, so if you've been plugging away at algebra, you definitely wrestled with the square root function. It's one of those fundamental graphs. But what happens when we change that little invisible 2 in the root to a 3? Well, today we're going to meet its much more interesting and flexible cousin, the cube root function.
Right, you know this guy, the classic square root function, y equals the square root of x. It's got that hard starting point right at the origin, it curves up and to the right, and it absolutely cannot handle negative numbers. It's solid, it's predictable, but it's really only telling half the story. So what happens when we make that one tiny change? We switch out the square root for a cube root. You know, that little 3 tucked into the radical sign. It changes everything. It literally opens up a whole new dimension for our graph.
And here it is. Meet the S-curve. This is the parent graph of our cube root function, y equals the cube root of x. Just look at it. It flows so smoothly right through the origin, and it stretches out in both directions, positive and negative. It's got a totally different vibe, a completely different personality than that square root graph.
Okay, so to really understand how to graph any cube root function they throw at you, we have to start here. We need to really master this foundational shape. So let's break down the parent function and see what makes it tick. The parent function couldn't be simpler. It's just y equals the cube root of x. Now, the single most important thing to get here is that it accepts negative inputs. Think about it, right? You can't take the square root of, say, -4. Not with real numbers. But can you take the cube root of -8? Absolutely. It's -2. And that one difference is what gives this graph its unique, two-sided shape. And because it can handle any number you throw at it, that leads directly to these key features. The domain, all the possible x values, is infinite, all real numbers. The range, all the possible y values, is also infinite. And that point in the middle, 0, 0, it isn't a starting point. It's called an inflection point. It's basically the spot where the curve changes its bend, kind of like a gear shift in the middle of the graph.
You know, probably the best way to lock in a new idea is to compare it to something you already know really well. So let's put these two radical functions, these two cousins, right next to each other and see the differences.
Let's just break it down, head to head. Look at the domain. Square roots are stuck at 0 and go up, but cube roots get to run free forever in both directions. That difference in domain directly creates their shapes. One is a half curve, the other is a full S-curve. And it all boils down to that one simple question. Can you use negative inputs? For square roots, it's a hard no. For cube roots, it's a yes, please.
Okay, now for the really good news. If you've ever had to shift a parabola, or a square root graph, or an absolute value graph, you already know all the rules for this. Seriously, the logic for transformations is exactly the same. We're just applying it to our new S-curve shape.
And here it is, our master formula. Looks familiar, right? Just like with all the others, h is our horizontal shift, k is our vertical shift, and that a out front handles any stretching or flipping. But here's the absolute key takeaway. That inflection point, the center of our S-curve, is always going to be at the point hk. If you can find h and k, you've found the new center of your universe.
Let's try one out. We've got y equals the cube root of x minus 1 plus 2. First thing, we hunt for h and k. Inside with the x, we have x minus 1, so our h is a positive 1. The number added on the end is a positive 2, so that's our k. What does that mean? A shift right 1 and up 2. So our new inflection point, our new center, is at 1, 2. All you have to do is plot that point and then just sketch that S-curve shape right through it.
Okay, let's try one with a little twist. Here, our a value, the number out front, is -1. That's our signal for reflection. It means our S-curve is going to flip upside down over the x-axis. Now inside we have x plus 3. Be careful here. The formula is x minus h, so x plus 3 is really x minus -3. That means h is -3, which is a shift to the left. And since there's no number added on the end, our k is just 0. So we put it all together, our new inflection point is at -3, 0, and we draw our S-curve flipped over.
All right, like any new skill in math, there are a couple of classic mistakes that are super easy to make. But the good news is, if you know what they are ahead of time, you can just sidestep them completely. So let's go over the big two.
Okay, this one is a huge conceptual shift. A square root graph has a hard starting point. The graph literally begins there and goes off in one direction. A cube root graph is different. It has an inflection point. The graph flows through this point. It doesn't start there, it doesn't stop there.
Think of it as the center of its symmetry, not its beginning or end.
And here it is. This is, without a doubt, the #1 error I see students make. Your brain gets so trained by square roots to worry about negative numbers and domain restrictions that it's just automatic. You have to actively fight that instinct, and remember, cube roots are free. The domain is all real numbers. Let those arrows on your graph go left and right forever.
So you might be thinking, okay, cool S-curve, but is this actually useful? You bet. Cube root functions pop up in some pretty interesting places. The most obvious one is the relationship between a cube's volume and the length of its side. They also show up in some formulas in meteorology for things like calculating wind chill. Basically, anytime you have a situation where something grows, but that growth slows down in a symmetrical way, a cube root function might just be the perfect model.
And that pretty much wraps it up. You've seen the shape, you know the transformation rules, and you know the common traps to avoid. So I'll leave you with one final thought to chew on. Picture that S-curve for the cube root. Now picture the graph of y equals x cubed. They look kind of similar, don't they? Almost like mirror images? Well, that's because they are. They're inverse functions, and that is a topic for another day.